All right, let's talk about something we all think we know, the tides. You go to the beach, the water comes in, the water goes out. It's like one of the most predictable things on the entire planet. But what if I told you that simple, everyday observation is just completely wrong?
Yeah, you heard that right. That's a direct quote from the one and only Neil deGrasse Tyson, and it just totally flips everything we think we know on its head. So, okay, if the water isn't actually coming in and out, what in the world is really going on?
Okay, so the first huge mental shift we need to make is all about motion. See, it's not the water that's doing the moving, rushing up to the shore. Nope, it's us. We're the ones moving, spinning on this giant planet through the water.
So try to picture this. The Earth's oceans, they're not a perfect, smooth sphere. Instead, imagine there are these two enormous, permanent bulges of water, one on each side of the planet. And the key here, the really important part, is that these bulges are pretty much just sitting there, staying put, held in place by some seriously powerful cosmic forces. So here's where it gets wild. This is the real motion. Our planet is spinning, really fast by the way, inside of these watery bulges. So that thing we call high tide, that's literally just your spot on the coastline rotating into and through one of those big bulges. It really just all comes down to our point of view, right? It totally shapes how we talk about things. I mean, we say the tide is coming in for the exact same reason we say the sun is setting. We know the sun isn't actually moving down. We're the ones spinning away from it. It's just a simple way to describe a much, much bigger, more amazing cosmic reality. Okay, so if these giant water bulges are just kind of hanging out, what's keeping them there? Well, this is where we bring in the two main characters in the story, our moon and, of course, the sun. The secret ingredient here is something called differential gravity, and it's not as complicated as it sounds. Think of it like this. The moon doesn't just pull on the whole Earth at once. It pulls a little bit harder on the side of the Earth that's closer to it, and a little bit weaker on the side that's farther away. This difference in the pull creates a stretching effect, basically pulling the oceans out into those two bulges. It's not just a pull, it's a stretch. You could almost think of it as Earth yoga. So who's the main yoga instructor in this scenario? Well, it's hands down the moon. The moon is the primary force, the main driver behind our tides. But the sun is a huge player too, kind of like a major tide assistant. And when these two get their forces working together, that's when things get really interesting. Yeah, this whole thing is like a cosmic dance between the sun and the moon, and how they're positioned relative to us dictates just how strong the tides are going to be. It is all about their alignment. And when they line up just right, we get to use one of my absolute favorite words in all of science, syzygy. Seriously, what a great word. It's when the sun, the earth, and the moon all fall into a straight line, which, you guessed it, happens during a new moon and a full moon. So, during this syzygy, the sun's gravitational pull and the moon's pull team up. They add together, creating what we call spring tides. These are the most extreme tides, the highest high tides and the lowest low tides. But then, when the sun and moon are at a 90-degree angle to us, their forces kind of fight each other. They partially cancel each other out, and that gives us the much weaker, more moderate neap tides. But here's the thing. Tides do way more than just move water around. They have this incredibly deep, long-term impact on our entire planet. In fact, get this, they are literally making our days longer. So how does that even work? Well, the Earth spins on its axis way, way faster than the moon orbits around the Earth. And because of that speed difference, our planet's spin literally drags that tidal bulge a little bit ahead of where the moon is. So the bulge and the moon aren't perfectly lined up. So you've got this bulge of water that's slightly ahead of the moon, and the moon's gravity is constantly pulling back on it, trying to drag it back into alignment. This constant tug of war acts like a giant gentle brake on the Earth's rotation, slowing us down just a tiny, tiny bit over time. And this isn't just theory, it's the whole reason we sometimes have to add a leap second to our clocks to keep them accurate. And we know for a fact this has been happening for a very long time. Scientists have found evidence in the coolest places, like in the growth rings on fossilized mollusks from millions of years ago. These rings actually record the daily tidal cycles, and they show that way back then, a year had way more days in it. The only way that's possible is if each day was shorter, which means the Earth was spinning faster. Okay, so now let's zoom way, way out. Because this whole stretching thing, this differential gravity, it's not just about our oceans.
It is a fundamental, universal property of gravity, and it works on literally every scale you can possibly imagine.
So what about that old idea that a full moon makes people act a little weird? Because we're mostly water? Well, here's the fun part. The tidal force of the moon across your skull is a real measurable thing. But it's about 1 trillion times weaker than the force your pillow exerts on your head when you sleep. So unless your pillow is making you act strange, I think we can safely say it's not the moon.
All right, so if the tide in your head is tiny, what's the most extreme example of a tidal force you can get? To find that, we have to go to one of the scariest places in the universe, the edge of a black hole. This is where differential gravity becomes the single most destructive force we know of, and it leads to a process with a perfectly and terrifyingly descriptive name: spaghettification. Just imagine it. If you were to fall feet first into a black hole, the gravity pulling on your feet would become insanely, astronomically stronger than the gravity pulling on your head. This immense tidal force, this incredible stretch, would just pull and pull, stretching your body longer and thinner, just like a piece of spaghetti. It would keep stretching you until the force itself was stronger than the molecular bonds holding you together, and you'd be torn apart into a literal stream of atoms.
So think about that. From the gentle waves you see at the beach to the slow, imperceptible breaking of our planet's rotation, all the way to the most violent end imaginable near a black hole, it is all the same fundamental force at work. Tides aren't just some weird thing that happens with water. They are a universal signature of gravity. And that means wherever you go in this universe, if you find gravity, you will find tides.